Hello there, class. Welcome to the next lecture in our Chem 112 series, and we are finally ready to move away from acid-base chemistry after all of the lessons that we've had. And we're going to continue along the trend with Equilibria. Specifically, we're going to start looking at solubility here. So this is a new type of K constant. Arguably, this will be a much quicker chapter, as well as I would probably say an easier chapter, just because the product constants are not going to be nearly as difficult to calculate in comparison to those of the acid-base reactions. So let's get started here. When we talk about solubility, one of the things that we can discuss is the ions and how well they will either break apart in solution or dissociate, or how well they come together and form what we would call a precipitate. Now, if you took Gen Chem 1 or Chem 111, you came across a chapter where there was a solubility chart, and we created general rules. So, for instance, we said any of the nitrate ions that are formed or coupled with any other type of cation are going to be 100% soluble. They'll completely dissociate. So you could kind of make the equivalence to that with something like a strong acid. So it will 100% dissociate into all of its ions, right? And then we had some of them that were considered to be insoluble, like a lot of the sulfates or the hydroxides were considered to be insoluble. Okay, and then there were exceptions to the rule. Now this was useful on a general level. However, it did not allow us to actually start putting numbers with this. We couldn't quantify it. It was more of a qualitative mix and match chart. So that's what the goal is going to be here. We want to put actual numbers along with solubility. So in order to do that, we're going to need to take a look at reactions and what is known as the solubility product. So the solubility product is written as KSP, SP standing for solubility product, and K is, of course, our equilibrium constant for a given type of reaction. So let's take a look at a simple example to start. What we'll work with is silver chloride. So this is one that is usually, if you look at that common chart, considered to be an insolubility. So silver chloride has small levels of solubility. So when we looked at those charts originally back in Gen Chem 1 and something said insoluble, what that meant was that we could safely form a precipitate when we would create a reaction with those various ions. But the truth is, now that we understand equilibrium here in general chemistry too, that a lot of these are going to have very, very tiny amounts of solubility relative to something like a nitrate ion, but it's not non-existent, so it's not completely insoluble. Okay? And that is what we're going to take a look at here. So here is silver chloride, and the way that we look at this, okay, similar to the acid, right? If you had an acid, which we were calling HA, it would go into equilibrium with H plus and whatever its conjugate base was. Well, here we're looking at solid compounds and their ability to solubilize in solution. And more specifically, it's usually water because we're dealing with aqueous ions here. So one of the reasons this becomes very easy compared to acid-base chemistry is that most of the acids were aqueous, whereas all of these are going to be solid material here. And when we have solids, solids are going to drop out of equilibrium expressions. We're not going to have to consider that when we're evaluating KSP, and that's going to be a very useful sort of dropout in the equation because all I have to do is some multiplication then. I'm not going to have any sort of denominator there. All right, and this is why it's called the solubility product, right? Because it's just the product of the ions that could potentially be in solution. So the way you could kind of view this equilibrium arrow is that this is soluble or solubility as I'm moving to the right, trying to form these ions. And then this is precipitate, which we can abbreviate PPT. Okay, going back this way. So that's when the ions start coming together. They crash out of solution and they form a solid, which we would call officially a precipitate in chemistry terms. So the KSP for the reaction that I've just written above would be equal to the concentration of silver ion times the concentration of the chloride ion. And that is all I would need for the solubility product. Okay? Now, because these are products that are able to be documented at 25 degrees Celsius and given a specific value, just like all the other equilibrium constants, you will find solubility charts. And when I'm talking about this, you'll have actual tabulated KSP values that you can find in the back of most of the books for chemistry classes. So that's similar to when we have Ka charts and they give the different Ka values for the acids. We can also have a solubility chart with KSP where they give the different KSPs for the salts that are considered minor in solubility or partially soluble in water, but not fully, because if it's fully soluble, meaning that these are 100% on this side of the equation, okay, a case like that is going to then have an enormously large KSP, and that would not be something that we typically consider. You're not going to get a precipitate then. Okay, so KSP is usually dealt with determining whether precipitates are going to occur and the type of how soluble your reaction is at a given state. Right, so I want to note here that when we are looking at these tables that I just mentioned at 25 degrees Celsius, you're not going to find certain salts, and that would be something like sodium chloride or potassium nitrate, right? Because if we consider these, right, all of these are going to be these types that would 100% dissociate, and so you wouldn't find them tabulated. Okay, now let's revisit Q. So if you remember, Q was originally called the reaction quotient when we were talking about general equilibrium process. And right here, Q is going to hold the same sort of, what do I want to say? It's going to have the same sort of effect as far as what we're using it for. It's going to be a placeholder while we're in search of KSP. But Q, which you could also call QSP if you want to differentiate it, is going to be known as the ion product. And Q will be a determination of the initial concentrations for your ions. So I could write QSP for this reaction as Ag plus, and then I'm going to just denote initial. Sometimes you'll see a little circle there, which means not. Okay, that's the way it's usually shown, right? And then Cl initial. And it is important to remember that this is not necessarily the concentrations at equilibrium. This is the initial concentrations of these ions. Okay, so the way that we can decide whether a precipitate is going to form or not is by comparing the Q value at the given state of a reaction to the KSP value of that reaction, right? So if we went back and we looked at the equilibrium chapter when we were first being introduced to this material, we would compare Q to Kc, and we could determine basically which way a reaction might shift or go, and whether products are favored or reactants were favored. So in a similar matter, right, because products and reactants, we can tell whether a precipitate might be favored or whether the ions will be favored in solution here. So the way that we would do this is we would say, first of all, if Q is going to be less than KSP, which is sort of your max out point, then the solution will be unsaturated, and if a solution is unsaturated, there will be no precipitation at that moment, okay, because you haven't hit the saturation point. Now when Q is equal to KSP, that means that the solution at that very moment is saturated, right? And saturated is a very specific state because it's got one value. Unsaturated is everything up until you hit the value of saturated, and then if you go past that, you can create a solution that's called a supersaturated solution. So when Q is greater than KSP, in that case you're dealing with a solution that has too much of the ion in it, and this is known as supersaturated. Now, when a solution is supersaturated, the way that it will attempt to get rid of some of the ions, because there's too many, is by forming a precipitate and removing them from the solution. So they crash out as a precipitate down to the bottom of whatever container they're in. And that would mean that a precipitate will form And more specifically, the precipitate will form, okay, until we get to a point where Q is going to equal KSP, right? So we remember we always try to head towards equilibrium. Well, in this case, precipitate's going to keep coming out of a solution until we're right at a saturated solution, and then no more at that point would probably come out. Okay, so this is a general look at KSP and the ion product and how they compare together. Now, there are other ways, specifically two other ways that we can typically look at solubility, and that is just general solubility itself. And when I say general solubility, we're talking about the grams per liter of saturated solution. Okay, and then we can also talk about molar solubility, and molar solubility is going to be, as you would probably guess, the moles in a liter of the solution, or the molarity. Okay, and specifically when we're looking at this, it's in 1 liter of saturated solution. Okay. So the last way of these three, which we just discussed, was that you could also look at the KSP. So you can kind of see this as akin to when we were dealing with acids. There are multiple ways that we can look at the strength of an acid. Perhaps we can look at its pKa, we can look at its Ka, we could look at the weakness of its conjugate, we could look at the pH, because that is a representation of how strong the acid is by releasing its protons. So there were multiple ways that we could kind of evaluate the strength of an acid, and in a similar fashion, there are going to be multiple ways that we can determine the solubility of a given compound, whether it be KSP, molar solubility, or just good old regular solubility, in which we use grams per liter. All right. So you need to keep in mind the general path here. You can move these back and forth. So grams per liter can easily be changed into moles per liter by using molar mass. Okay. And then through equilibrium, we can relate the molarity from moles per liter into KSP. And likewise, if I know KSP, I can find the moles per liter for the ions, and if I know the moles per liter for the ions, I can find their general solubility in grams per liter, right? So this can go back and forth in this fashion. So let's take a look at an example, right? We'll use silver bromide in this example. So we just looked at silver chloride above. Now we're going to look at silver bromide, okay, as a solid. Now silver bromide as a solid, let's try to find the molar solubility, and then we'll try to find the just regular solubility. So what we'll need here is the KSP. You can look in the back of the OpenStax chart to find the KSP value here. So the KSP value that I found in the OpenStax chart was 5.0 times 10 to the negative 13th. All right, and this value is going to be equal to the KSP for AGBR. Now, what I want to do is first set up the general dissociation or solubility equation. I know that AGBR as a solid can go into silver ions as well as bromide ions. Right? Now keep in mind, a lot of these examples right now are 1-to-1. If any of these had 2 in front of them, because we have to have balanced equations, then you need to account for that when you're dealing with any of your products. We still raise exponentially to any coefficients that are there, stoichiometrically speaking. So don't forget about raising your values here. Okay, so for ice, if we set up an ice chart, we can skip out on the AGBR because solids are not included in our equilibrium discussion. This would start out as 0 for both of these, right? So I have some solid, I get ready to put it in, and at time 0, right as it's starting to hit the water, there is no silver and no bromide ion concentration. Okay, so I suppose we could say minus X because some of this will dissociate But what's more important here is we've got plus x and plus x. And then at equilibrium, again, we don't concern ourselves with the concentration of something not in solution. So I can't really calculate AgBr at equilibrium, but I can certainly find the ions. And through the ions, I could find the molarity of AgBr, right? So because if I can find the molarity of this and the molarity of this, then I know the moles of each of them. And if I know the moles, then I can find the moles and therefore the molarity of the AgBr. Okay, so I'm not going to find it directly through the ice here, but I can indirectly find it by solving for the products and relating it back to that. Right? Now in this case it would all be 1-to-1. So the way that I would move forward here is I would say KSP, which we said was going to be 5 times 10 to the negative 13th, is equal to x squared, right? Because it would be Ag plus times Br minus. So I need square root for both of these. And if I take the square root, I end up finding that this is equal to 7.1 times 10 to the negative 7th molarity. Right? So this is the answer here. And this would be the molar solubility of this compound. Okay, now the next thing we said was, what about just the regular solubility? So if I wanted this to be grams per liter, well, again, going up to this chart, I used the KSP in order to find molarity, which is moles per liter. So now I just need the molar mass to get into grams per liter. So what I could do here is I could rewrite this and say 7.1 times 10 to the negative 7th moles in every 1 liter. Okay. And then I want to cancel the moles, so it's going to be 1 mole. And then I need the molar mass of the silver bromide. So if you were to add up the mass, or you can check it online quickly, it is 187.77 grams for every 1 mole. And so if I solve that, I find the solubility, again moles cancel, so I'm now in grams per liter. The solubility is going to be 1.3 times 10 to the negative 4th grams per liter. All right. So that is going to conclude this lecture because it's getting close to about 20 minutes here, so that's where I usually like to wrap it up. In the next lecture, we will briefly talk about something known as the common ion effect. So what happens if you're looking at the solubility of a certain material and then another material is introduced that has common ions. So we'll look at the common ion effect, and then we also may briefly discuss whether a precipitate will be forming in solution or not when you mix 2 materials together. So you've probably seen reactions like this. You have 2 soluble materials, you pour them together and a precipitate forms. We'll either practice problems like that in class, or I will try to include one in the next lecture. So until next time, thank you for your attention, and I will see everybody in the next lecture.